Success. All right, so from your carbohydrate chapter, glucose is the 6-carbon sugar with an aldehyde group. You did a bunch of different work looking at the alpha and beta form of glucose. This one over here is cellulose. This one over here is glycogen. And glycogen is the one with alpha 1,4 linkages, which your body is able to digest and break off little pieces of glucose from it. Where you had the homework question about cellulose. Cellulose has beta 1,4 linkages, and we can't break those in our system, which is why the question about celery, it's your body doesn't really gain or lose anything by it, it just really passes through. It is great for your colon, cleans things out, but not really great for much of anything else. Okay. So, gluconolysis takes place in the liver. So, right, in our body, glycogen is the storage molecule of glucose. In the liver, glycogen can be broken down to free glucose molecules. That can then enter glycolysis. So now we have our free glucose molecule. We are ready to enter glycolysis. That's mostly okay. So glycolysis is a 10-step reaction. Ten-step reaction with 2 stages. The first stage is an energy investment stage, and this is reactions 1 through 5 are our energy investment stages, where glucose is phosphorylated and then cleaved into 2 3-carbon molecules. Stage 2 is reaction 6 through 10. And that's the energy recovery stage. Those 2 3-carbon molecules of glyceraldehyde 3-phosphate are finally converted to pyruvate, and it makes 4 ATP by the end. Bless you. So, since this figure is kind of hard to read, I'm going to write on a separate sheet of paper so we can all look at together, and then we'll investigate every reaction individually. All right. All right, so for glycolysis, these are the things that you're going to need to know specifically. The names and structures of all the intermediates, the energy investment points, and the cofactors and coenzymes. What are they, and where are they being used? All right, so as we walk through our reaction, all right, so we're going to start off glycolysis with our glucose molecule. All right, so here's our carbon number 1. That's our anomeric carbon. Carbon number 6 over here.
Are these the intermediates or?
That's the starting thing.
So this is like using the steps?
Yes.
Okay.
Yep. All right, so glucose enters glycolysis. Its first enzyme it runs into is glucose 6-phosphate. Any guesses? Oh, sorry, I wrote that wrong. That's its first intermediate. I want to use hexokinase to make glucose 6-phosphate.
Is that hexokinase?
Yep, HEXOKINASE. I got ahead of myself in my notes. So hexokinase and magnesium 2+ in the presence of glucose makes glucose 6-phosphate, which means we are phosphorylating our glucose, which means we will need an ATP at that step. So as the name implies, we've now phosphorylated the glucose at the 6th carbon. So now we use the enzyme phosphoglucose isomerase. What does an isomerase do? Makes an isomer of it. So it doesn't change what atoms are there, it just rearranges the position of the atoms. So we were a 6-membered ring, we will now be a 5-membered ring. Now that's still 6. Now this was 1. So 1 is now, was here part of the ring, and now it's outside the ring. No, it's the O that was here. Oh, hold on, let me see. No, that's right. We'll see why in a little bit.
So it does have.
It does have an extra OH group. Yep.
Where was the one? Sorry.
Was here. Our anomeric carbon was 1. No, it's over here. Yeah, there's just as many OHs. 1, 2, 3, 4. 1, 2, 3, 4. Just, yep.
The way it looked.
Yeah, yeah. It looks funny, but now it's just, it was one of the ones that was over here. No, it's off to the side. And so what's our 5-membered sugar called? Fructose. So that name should make sense. It was glucose 6-phosphate, and now it's a 5-member ring, so now it's fructose, still 6-phosphate. Oh, no, I'm ahead of myself. Sorry, not aldolase yet. We need to use phosphofructokinase. Which makes sense because we have fructose over here, so we want to use the phosphofructokinase. And just like the hexokinase, it is going to phosphorylate. So very similar to that first step where we had glucose, hexokinase phosphorylated it. Now we have fructose 6-phosphate. We use another kinase. And now we have a double phosphorylation. And it has a great name, fructose 1,6-bisphosphate. So it's a fructose molecule with 2 phosphate groups, 1 on the 1, 1 on the 6. Yeah. Ooh, we will talk about that. The magnesium is a cofactor that we'll need when we look at the individual mechanisms what the magnesium is used for. But in general, it's to let the ATP lose 1 phosphate group so it can come onto the molecule. Yeah.
So on the fructose 6-phosphate, on the first carbon you have an OH.
Yep.
Now you have an H on the next one.
Oh, let's see which one is right. Should be an OH. Yep.
It's a biphosphate, the fructose 1,6.
Bis.
Okay.
Yeah. For whatever reason, it should be bi. Like bi would make sense, like 2. They went with bis. I wasn't there, I would have set them straight. This doesn't make any sense. So now we're going to use the enzyme aldolase. And aldolase is a cleaving enzyme. So at this step, we are now going to cleave this into our 2 3-carbon molecules.
You call it cleaving?
Cleaving, yeah. Cut in half. Now we have our 2 3-membered rings. glycer. One's going to be glyceraldehyde 3-phosphate, and the other one is dihydroxy acetone phosphate. And that is the end of the energy investment stage. So we've used 2 ATPs at this point. That's all the energy we're going to invest in the cycle. The rest of the steps, we'll get energy back out of the cycle. Maybe I just scoot up. Okay.
So do you want us to
So anywhere that's ATP is an energy investment.
Okay.
Anywhere we get out an ATP would be an energy return.
Okay. So just putting the ATP is sufficient, like that indicates that it's energy. Okay.
Yeah. Let's see, where am I at? I just did that. So now we'll use the enzyme glyceraldehyde 3-phosphate dehydrogenase. To make 1,3-bisphosphite glyceraldehyde. Oh, sorry, glycerate.
So this part, starting from here, is taking energy out.
Yep. From here on out, we'll see where energy starts to be released. So one of the steps will be this glyceraldehyde 3-phosphate dehydrogenase. Uses inorganic phosphate and NAD+, and will give us back an NADH. All right, so now our 1,3-bisphosphate glycerate is going to interact with phosphoglycerate kinase. And now we start getting an ATP back out. All right, so just like we've done all these kinases before, these kinases can either give or take off a phosphate group. It is going to cleave off a phosphate group off of this molecule. And so where it was 1,3 bisphosphate glycerate, now it's just 3 phosphate glycerate because it's lost the other phosphate. All right, the next enzyme is going to be phosphoglycerate mutase, which, as its name implies, is going to just mutate it. It's going to just reorganize where all the atoms are. So it was 3 phosphate, then gets mutated, now it's 2 phosphate. We're real close to being at the end. Then we're going to use enolase. We're going to remove the water, and we'll need some magnesium at this step, and we'll see why when we look at it more in depth. So you can see that we cleaved off that water portion, the alcohol, we cleaved it off some water. Oh, you're right. So that's now phosphoenol pyruvate, which means we are one step from the end because our final product needs to be pyruvate. That's not right. Really not right. So those are in general. Yeah, question first.
Once you make 2 pyruvates, that kind of happens twice.
Right, so back up here, when we made 2 3-membered carbons, each of them enter the cycle, and so I'm just showing one going through, but in reality, both of them can come through. And so for every 1 glucose, you get 2 pyruvates.
Can you show the last 3?
All right, so that was all what was on this little tiny chart, which is also in your book. If you feel like you missed a step, it's this right here. It's just very tiny, very tiny. It's better in your book. So what we're going to do for the rest of today's class, at least, is walk through each one of those steps and see what's going on. So we'll start off with hexokinase.
So those are the 9 intermediate.
Yes, so these are the 9 intermediates, the enzymes, the energy investment, which would be an ATP, energy return, which would be an ADP going to ATP, where all the magnesiums are, 1 K plus and 1 NAD plus. Yes, Sarah?
Is it okay if we just know the abbreviations?
That's okay if you know the abbreviations. Yep, that's fine. So if you know these as 3PG and 2PG, and that's fine. I may, in the multiple choice section, ask you the other way, so as long as in your head you know what they both mean. But for writing it down, yeah, there's official, yeah, the official ones, yep. Yep. All right, so let's look at hexokinase first and see what's going on in that mechanism. So hexokinase, like we talked about on, what day is today? Monday. Like we talked about on Monday, this is one of our irreversible steps. So we have to have a step that only goes in one direction. So once glucose enters the reaction, it can't come back to being glucose. It is one direction only. So hexokinase transfers a phosphoryl group from ATP to the glucose ring. So now we had glucose, now we have glucose 6-phosphate, which tells you that the phosphate group is on the 6th carbon. This should help with all your learning of these reactions. The job of a kinase is to transfer phosphate groups. So every time you see kinase, it means it's either adding or taking off a phosphate group. So we had hexokinase, we had pyruvate kinase, we had phosphofructokinase. Anytime you see, phosphoglycerate. So anytime you see kinase, it means there's a phosphoryl group being added or removed, which is always in conjunction with an ATP or an ADP. So those reactions happen together. So if you see kinase, you know there's going to be a phosphate group transferred, and there must be ATP or ADP in the vicinity. So those are the guys that are either going to take it or give it back. Meltage of this reaction is approximately negative 16.7 kilojoules per mole. If it's negative, what does that tell you about the directionality of it? Yeah, it's definitely going to products. So that might also help when you're thinking about these reactions. It has a strong negative delta G, which means it's only going to go to products. It doesn't have the capability of returning to glucose. Then Victoria asked me earlier about why do we need all these magnesiums. This little picture right here is why we need all the magnesiums. So ATP and glucose in the active site of hexokinase needs to have a magnesium also available. The magnesium is going to hold on to the negative charges of the phosphate groups on the ATP so that the glucose only cleaves off one phosphate group. So we need the magnesium in there because it's going to stabilize those negative charges and allow glucose just to attack one phosphate group. Which is why, in general, every time you see a kinase, you'll also see magnesium. So kinases, ATPs, magnesiums all work together. So why do we put that phosphate group on the glucose? Phosphorylate. So we only have glucose transporters in your cells. We don't have glucose 6-phosphate transporters in your cell. So now we have phosphorylated it, it's negatively charged, and now unable to leave, which is the other part, being irreversible. It now has to do the next set of mechanisms. Questions on step 1? Hexokinase, fun facts about hexokinase. Let's talk about some fun facts about phosphoglucose isomerase. All right, phosphoglucose isomerase, its job is to convert glucose 6-phosphate into fructose 6-phosphate. So to change our 6-membered ring to a 5-membered ring. This, as the name implies, is an isomerization reaction. So we've now converted from an phosphorylated aldose to a phosphorylated ketose, which is good because in the next step we're going to need an enzyme that works best with a ketose. In the previous reaction, you may not have noticed the arrows. There's a strong arrow forward, right, which means irreversible. What's going on here with my arrows? Forward and backwards, at equilibrium. So what is the delta G for this reaction? Best guess, about 0. So this reaction is considered freely reversible. That Le Chatelier is going to play a bigger part in this than thermodynamics. So when we get a buildup of glucose 6-phosphate, it'll make more of the fructose 6-phosphate. It'll force it that direction. So this reaction is going to be concentration driven rather than thermodynamically driven. Kinetics, really. Kinetics. Yeah.
Is that so like that wouldn't happen unless you have this like more self-control that happens?
We can get a buildup of fructose 6-phosphate, yeah. From a few different pathways, we can get a buildup of fructose 6, and then it would push it back to the glucose 6, which we can do some other things with glucose 6. So this is one of those spots where multiple cycles kind of interconnect. And so this one is one of the intermediates that can go do other things, or it may be coming from a different cycle to enter glycolysis. So it's going to just depend on what's going on with those other cycles. Any other questions about this step? This is pretty straightforward. PFK. This enzyme is awesome. The best enzyme, well, not the best, one of 2 best in this step. All right, so phosphofructokinase phosphorylates phosphorylates to be more complete. F6P2. Okay, so we have fructose 6-phosphate. In the presence of phosphofructokinase and some magnesium, we get fructose 1,6-bisphosphate. Mechanistically, it operates similar to hexokinase in that needs an ATP and magnesium 2+. Both of them are required for both those steps. What's the direction of my arrow telling me about its reversibility? Not reversible. Okay, so delta G is definitely negative. It's not a reversible step. PFK catalyzes one of glycolysis's rate determining steps. So this is one of the first steps we see where there's definitely an on-off mechanism for the enzyme. So PFK's activity is enhanced by the presence of AMP, which is adenosine monophosphate. And then PFK is inhibited by the presence of ATP and/or citrate. So why, oh, go ahead. We'll call activate. We'll just call it activated. To me, I meant rate enhanced. Oh, activated. Yeah. No. Activated's good too. If you want to think about it in terms of opposites, like activated versus inhibited, yeah, that would be true. Or the rate's enhanced, like it was not going and now it's going faster.
That's not like regulated by it.
It's not. No, it's not exactly regulated by it. Yeah.
If it's inhibited by ATP, then how does it inhibit ATP?
That's an excellent question. Excellent question. So, what's the best picture I have for this? I'll write it here. Okay, so we'll work our way through this. One, PFK has 2 ADP binding sites. All right, so the enzyme PFK has 2 ADP binding sites. The ADP binds to PFK and causes a conformational change in its active site that promotes catalysis. Trying to see which one it's going to be. I'll do this first, then I'll show the next slide. So just like hemoglobin, there's going to be an R state and a T state. In the T state, either phosphoenolpyruvate or ATP binds and prevents the fructose 6-phosphate from binding. So, which is this little figure down here. These T and R states are in equilibrium. And ATP is both a substrate in that it's needed in the active site to phosphorylate fructose 6-phosphate to fructose 1,6-bisphosphate. But it can also be an inhibitor in that it turns off that pathway. So, glucose making fructose 6-phosphate, you need ADP to bind. But if there's a lot of phosphoenolate pyruvate in the system, it turns off that enzyme and stops the reactions farther down. And this would be when it's working correctly. So, when glycolysis is already producing plenty of phosphoenolpyruvate, which is the step just before the end, and or there's already a lot of ATP in your system, right? Because one of the main things for glycolysis is to make ATP. So if there's already a lot of ATP, then PFK is inhibited. So what we call, in this case, phosphoenolpyruvate is a feedback inhibitor. Which we'll see a lot of other feedback inhibitors later on in our cycles, or if we make a lot of stuff at the end, it tells the cycle at the beginning, slow down, we don't need any more. And then when the substrate concentrations decrease again, it turns the cycle back on. We'll talk more about PFK Friday. Yes, Cindy. I think the stuff we mostly did on Monday. So metabolism, intro to metabolism stuff.